So good afternoon, everyone. This is lecture number 33, E524 Digital MOS LSI Circuits, and today is November 9, 2020. So we were talking about various memories. In memories, we have learned the structure of memory at the top side. In that memories, we were learning about SRAM, and we learned that we learn about this memory which has bit and bit bar line. Other than that, Q and Q bar as a state, and word line to select particular cell. And we were talking about the reading part, and we learned that there are various transistors whose names are like A1, A2. These are the access transistors, and these are P1 and P1. So P1 is for PMOS transistor and D1 is for the driver transistor, and this is similarly D2 and P2. So we learned that if you want to do the efficient reading operation of SRAM, the W by L of D1 has to be much larger than W by L of A1. This is because of the fact that there are like two transistors connected at the node Q. Either of them can go to, like, if this is bit line is 1, like, because it's precharged to 1 earlier and thereafter it's changed. So if Q is written with 0, then this bit line needs to be changed, and to change that it can be changed only through the access transistor A1, and if the 0 is available at Q underscore B, then it has to be changed through access transistor 2. So in that case, access transistor 1 and access transistor 2 both has to be at a smaller value compared to D1 and D2, and D1 and D2 will be a high value, just to make sure that these values won't change, right? And it will remain at 0 if it is at 0. And because of this cross connection, so cross coupled connection will make sure that if this is Q, then this will become Q underscore bar. Of course, it will take some propagation delay, and through which you can have the settled output. In this particular case, if you miss to do this one, W by L of D1 and W by L of A1, the way it is required, in that case, it might happen that, look, this Q can change the state of the P2 and D2 such that Q underscore B will be changed, and if Q underscore B will change, then Q will change, and it's a positive feedback. So thereafter it will be changed, and this is happening with the fact that where you are keeping the switching threshold of P2 and D2. Right? So if P2 and D2 switching threshold is somewhere here, and this Q is trying to go above this value, because when this is going to be on, means A1 transistor is going to be on and this is also on, at that time when VDD is trying to discharge to 0, at that time Q will also try to go upside, because both are having the coupling. So because of enough coupling, this bit line is going down, and Q will also try to reach to the value where bit line is, but it's a fighting between these two transistors. Through the resistances you can decrease it, but you cannot make it 0, always. So this Q will also try to go up, and if this Q reach the value where the switching threshold of transistor P2 and D2 are there, then what is going to happen? This will be qualified as logic 1. So you will see some bump over here, and then it will go up. But when it's going up upside, at that time this Q bar is going to become, so if this is becoming 1, this becomes 0, and that will make this transistor off. And because of that, this will become having no connection with the ground. So in that case, this will not happen, but it's going up. And of course, Q will become also 1. So this is going to happen if this P2 and D2 switching threshold voltage has not been designed such that it's above the value of Q. So if it is lower than it's a wrong code. So to save that, we also agree that P2 and D2 switching threshold has to be much higher than Q. Has to be greater than Q, right? So if you guarantee these two, then you can read the values written in this cell at Q and QB very efficiently. So now the next line is the writing part. Now let's assume that I want to write. Means I'm going to write it through bit line or maybe bit bar line when I am doing the evaluation, or you can say the reading and writing operation in phase 2. Because in phase 1, it's a pre-charge where bit and bit bar both are equal to VDD. Whereas in phi 2, you can perform the operation of read and write. So read, already we learned how to do the reading, but how to do the writing part, let's look at that. So as already mentioned over here, let's make the new okay. So in the same circuit, I want to write down the value. So it's going to be written when word is going high, by the way. Okay. Before word is not going high, this is not going to happen. At that time, it's a pre-charge. Okay. Or you can say that before that, bit and bit bar are going to be logic 1. So bit bar and bit both are at logic 1, right? So this is going to be there. Now let's assume that I want to write down 0, means here, because that is what, sorry, I want to write down Q as 1. If I want to write down Q as equal to 1, how can I write it down? Let's start with that. So if I'm interested in writing down Q equal to 1, I need to make bit equal to 1, which is already 1 right now. And when I'm connecting this, note that when I'm connecting this word with the same theory which we are applying, that look, I'm going to connect it such a way that A1 and these two transistors will be there, but D1 has more W by L compared to A1. So this transistor is going to be 0. It's not going to be here and there. It will be staying at 0. So make it 1. It's only possible if you change the state over here, right? It's not possible from changing from here that you are writing 1 means it's going to make this one equal to 1. It's not possible. So what we can do, we have to analyze it through this side. If you are interested to do this one, bit bar, if this is 1, bit bar goes to 0. So let's understand that this is bit and bit bar is going 0, right? This is what I am going to write over here, 1 to 0. Earlier it was pre-charge and now it's 0. If it is 0, look, still there is connection between D2 and A2. This node cannot go to, the value where we want because of this one, which is the case over here, right? So because if this is 0, this side is also 1, this side is also 0. So there is a fighting between these two transistors, right? So what I can do in that case, I'll make sure that P2 is lower value compared to A2, so that this can go here, but not this one. Right now there were 3 possibilities. Right. So let's assume that when you were writing it earlier, this was 1. So in that case, there are 3 different transistors are here, maybe partially on, maybe fully on. So if they are partially on, in that case, these two are playing the role over there. Even if you'll make sure that this transistor is off by making sure that Q equal to 0, even if it is earlier state, then these two transistors will be there, which are fighting with 2 voltages, bit bar equal to 0 and VDD equal to 1, right? So it's actually fighting between these two. So what I want to do, I want that this particular transistor should be strong as compared to other transistor which is weak. If I want to make it weak, then I need to keep W by L of P2 lower than W by L of A2 by making this A2 transistor stronger compared to P2. So this will make sure that 0 can go here with given propagation delay. So at Q underscore B, you can observe that it's going from 1 to 0 and Q goes from 0 to 1 because of this feedback loop, right? And this is also the same way which we were doing, that P1 and D1 threshold has to be actually set such a way that QB is going to be going from 1 to 0, right? So for doing that, you know what's the answer is, right? So this is how you can write the cell. Now let's look at the writing if it is happening in a column. So earlier we were doing in SRAM read cell, same thing was there, and we had this kind of setup, right, where output were driving by the high skew inverters, and in the case of write, we are going to have some write driver. So there are 2 possible things. One is given here in this option number 2, and this is option number 1. Option number 1 says that if I want to write down if both are 1, then both the lines, bit line and bit line bar, are going to be on. Now the whole thing is depending on what are these values. If data underscore S1 equal to 0, then this transistor is off, and because of inverter, this transistor is going to be on. In that case, this line is written with 0, and this line cannot go anywhere because of the bit line capacitance, which was already pre-charged to. So this is bit line cap, which was already charged to VDD, so it will not go anywhere because somebody has to discharge it, right? But there is no discharge path at all, so it's not going to be discharged, and it will be remain at VDD. Similarly, you can flip the thing, and these two transistors will be on and off according to what value you are giving. So in case of one, this transistor is on, and this line is connected to 0, and other line is going to be connected to VDD, right? So that is how you write down the complete column cells, right? So in your case, which project I was giving you, where it's 8 cross 8 things, where there are almost like 8 rows and 8 columns. So if you want to write them 8 columns together, you need to do what we have done right now. So you have to follow this way, right? And this side and this side are row and column decoders, which are going to control particular cell in a particular position, read, write, or whatever you want to see, right? Other than that, there is also other thing where like you can use some combination logic, which is going to tell you that which one is going to be on and off. So you can apply that. So it's very easy. So I'm not discussing that, but it's a very simple thing, right? Yeah. Now the main part of the any memory is its read and write stability. So it's all depend on whether you can write it down in so much of margin. Like earlier we were having something called just a noise margin, but for the memory it's known as the SNM, which is known as the static noise margin, SNM. It has to be good enough so that you can read, write, or hold. There are 3 kinds of basically margin. One is the hold margin. When there is hold, look, cell has to retain its value. Means I'm talking about this cell. When its word is not connected, these will have some value, Q and QB. So those value has to be hold, right? For some times, and as well as for a given voltage value. So that's the hold margin. Some people sometimes call it hold time also, but do not get confused with the hold time, which is for the case for timing constraint. That hold time is different than what we are talking about right now. So it's better to call it hold margin rather than calling it hold time, right? So hold margin is related to the SRAM stability. The second part is the read margin, and third part is write margin. So 3 major things where you need to see that what is the margin, and those margins are known as static noise margins. So all are SNM, but for different cycle. One is for hold margin, where you are recharging the bit and bit bar line, where one line is not connected, and what value is retained by the cell, that's the hold margin. Next one is the read margin, whether we can read it or not, that's the read margin. And the last one is write margin. So which are determined by the static noise margin of the cell in its various nodes of operation. Is a cell should have 2 stable states during hold, because in hold you are going to have 2 things only, either logic 1 and logic 0, which is going to be hold. In read state also, you don't know, but you might have logic 1 and logic 0. But in the case of write operation, you are going to have only one operation. You are interested in either writing logic 1 or logic 0. So that particular noise margin you need to see. So the noise margin, the static noise margin, measures how much noise can be applied to the input such that it does not change the value, right? So that is what we are going to do. And for that, we are going to study some of the important thing for a cross-coupled inverter, which are in positive feedback. If you remember, if this is V1 and this is V2, we learn that V1 with respect to Vt will look like this one. And V2 with respect to V1 look like this one. And merging both of them will look like this one. By the way, this diagram is going to be known as butterfly diagram because it looks like butterfly, right? Okay. Here, the most important part are three different points. Two are stable points and one is metastable. And we also learned that around this C point, how much noise you can add, so that because of the positive feedback, it will either go to point number A or point number B, right? So this particular window, let's say if it's a 0.4 volt, then that's the actually capacity of this cell that it can sustain so much of noise, or it will be declared as logic 1 or logic 0, right? So this and this are going to tell you what are the hold time, because this right now is not in reading mode or in writing mode. But if you have two transistors connected and if you are reading it, then this will be for the read margin. Right now it's for the hold margin, right? So this is very important that in such condition you might have equal squares or you may have the different one. It depends on how you are designing it, and you know how to design such kind of things with the noise margin high and low one, or with the value of the resistances, right? So in this case, like this is same thing when we are talking about the hold margin. In that case, you have two inverters back to back, one side V1, one side V2, and both are acting as noise. Then you will have such kind of diagram which is known as the butterfly diagram. This particular line of symmetry is decided by the switching threshold. Notably, both the characteristics are same, like either you are plotting V1 with respect to V2 or V2 with respect to V1, both are same, right? More or less. It will give the same answers, but it's all depending on these inverters' strength, whether they are weak or strong, or if they are not equal. If they are equal, then more or less you will get the symmetricity which you are seeing on the right side. So now let's assume the fact that now the whole margin is quite easy with the fact that you have 3 points A, C, and B. But let's assume that you are not interested only in whole margin, but you are interested in read margin. If you are interested in read margin, look at the diagram. How does it look like? So bit and bit bar were pre-charged before going in read operation. So both are pre-charged to VDD, and both are going to be connected with word lines. Here you are going to have two inverters back to back. And this is V1, this is V2. Right? For such kind of circuits, it's better to divide that in two parts or half circuit. Right? So it's exactly symmetric, up and down. So when you want to plot V1 with respect to V2, you are going to use one of the half, and V2 with respect to V1, the another part. So what is going to happen if I am drawing with V1 with respect to V2? Let's say V1 is changing and V2 is, or better thing is I'll keep it other way around. Okay, both are same actually, so that I can cover this transistor. So these two are excess transistors. Now what is going to happen? If I want to draw the butterfly diagram, how does it look like? If I am looking at V1 and changing from 0 to VDD, right? So V1 is changing from 0 to VDD. At the first hand, when I'll redraw this diagram because the more realistic diagram is this one. Right? Both are connected to VDD as shown over here. Right? So in that case, what is going to happen? If V1 equal to 0, V2 is going to be VDD, right? No problem. If I'm increasing this, it follows the curve which we were seeing. But the problem occur when you're going a bit other side. When you are going beyond VDD by 2, what is going to happen? If you are going more than VDD by 2, this transistor is on, and of course this transistor is also on, right? Because of VDD is already connected there. When you are doing this, at that time VDD is also here, and because of that, you cannot reach exactly at 0. Because there are two transistors which are fighting with each other, right? Because of the presence of this transistor, actually this voltage does not go to 0, but there will be some drop. So it will be little bit higher than some value. Let's call it V. When you are going in other side, where V2 is here and V1 is here, where V1 output includes the excess transistor A1, it's going to give you problem when actually you are going at the higher voltage side, right? So it will have the same characteristic, look like this one, but maybe for your understanding, I can draw. So this is curve 2 when it's V2 with respect to V1, and other one is curve 1 when V1 is varying and you are looking at V2. So because of one extra transistor, which was actually the fighting between VDD and ground, it's going to give you such kind of butterfly effect. So earlier it was like this one when it was, sorry, when it was whole time, but because of this extra transistor, this window gets smaller compared to the whole margin. So this read margin, in a case, we are going to have less than the hold margin. Not good, but we cannot avoid it because that's the property of 60 SRAM cell. It's happening because how you are reading it. It's all depending on that. You can see that this window is getting smaller. Right? Now, if you are interested in writing it and you want to see the right margin, what is going to happen? You are going to have only one state, either logic 1 or logic 0. So you can see over here that the first curve, which is V1 with respect to V2, when you are changing, so this is bit and this is bit bar, one of the line you are interested in writing down, right? When you are writing one of the line, if it is 0, no problem. One side, if it is 1, then again there is a fighting between two transistors, XS2 transistor and the driver transistor. So any one of the side, this will happen where you are writing logic 0. It's not going to happen, but logic 1 side, this is going to happen. So when it's happening, it's exactly the curve number 1, which is V1 with respect to V2. It's exactly same what happened to the case for read margin. But if you're looking at other side where particular line is connected to 0, so other side is not this. This is always going to be less than 0. Of course, there will be fighting between this transistor and other transistor, or I would say that the transistor of this one, there might be fighting between these two transistors, but they are not allowing this to be on in such a way that this particular node is going to be lesser than P2 and D2. So lesser than P2 and D2 means it's going to be less than what voltage is required. So you can see over here that for a 1 volt, 0.5 might be the switching threshold. And your output remains below the switching threshold so that it can qualify the logic 1 or logic 0 efficiently. So here you can see you have generally the good right margin is there. It's all depending on how you are designing the access transistor, the driver transistor, and the PMOS transistor. So as per the thumb rule, D1 and D2 should be higher. The next higher guy has to be A1 and A2. And P1 and P2 has to be the smallest one, right? Note that when you are doing all these things, it's with respect to resistances, and you have to incorporate the mobility of NMOS and PMOS so that you can get the accurate answer. This is not trial and error, but you have to work upon it, right? So that's the completion of the SRAM cell, how to read it, how to write it, and the most important part is its stability. So cell stability depending on 3 factors: hold margin, read margin, and write margin. In all these 3 margins, you need to use the butterfly diagrams, and this window is going to decide whether your design is good or bad, right? So I'm not going into much into this because These are very straightforward things, like you can draw the stick diagram, and for a given stick diagram you can make the layout, which is the top view. Note that this particular dotted line indicates that it's one cell. Okay, other things will be like overlapping with the next particular cell, so that we can save the area. Note that one more important part over here is we are not going to change the orientation. Means if this is a gate and this is drain and source, if you choose to make this way, do not make the transistor this way, because both are not identical, right, in terms of capacitance, and lots of problems will occur over here. So it's better to follow the same orientation which we want, right? And of course, when you are drawing this, you have to make sure that like we have to have the smallest area as possible, right? So that we can look, everything is depending, like if you are increasing this cell area, it will increase the overall memory area, right? And hence it's all about money, because this is very expensive thing, right? Now you might be interested in one more thing. If you are working at you might be working at low voltage. So VDD is low voltage, then this might not work. This 60 SRAM, 60 SRAM cell may not be the proper solution, because it's including the cross-coupled transistors and cross-coupled inverters. That will not give you the reading and writing property properly, because one of the transistors is always fighting with another one. If you remember, this thing is happening because of the fact that this is actually extra transistor is there, which is connected to VP. Now, how to get this particular thing, right? So I want to achieve this butterfly diagram. This is one thing, and this VDD is going very low value, maybe 0.9, 0.8 volt for a given technology node. So in that case, as you are going low voltage, you might not get the output as you want, and sometimes it happens that you are working not in the required mode of operation, but it's working in sub-threshold. So your transistor might be conducting in sub-threshold, and in that case, you need to think about some dual port technology or the dual port method. That dual port method allows you to reading the cell directly. Means like this. You might have bit line and bit line bar. You might have the word line, which is actually controlling only and only these two transistors, E1 and E2. Whereas there is another word line, which is read word line. This read word line is only controlling this part. So depending on what input is available here, that will be amplified. Look at this. There is a transistor. If you are applying over here, if this is a 0.9 volt supply voltage technology, and if this is not 0.45 but 0.25 or 0.35, it's going to be amplified other side. It's acting as a small common source amplifier which has the gain of GMRO. So the intrinsic gain will allow you to get the full scale value, either VDD or ground. So if this value is very small, then this will go to the value which is VDD, because from here to here it's a negative gain, and from here to here, if this is VDD, this will go to 0, right? So small change can be reflected over here, and because of this particular line, what you are going to read over here, it's VDD and ground without having any problem. So this is going to give you efficient read operation, and of course it's going to increase read margin, which is going to be exactly equal to what was happening for the hold margin, because you are reading directly from the cell. You don't use access transistor. If you are using access transistor, then its whole story is coming, and one of the side is connected to VDD, and like because of this recharge operation, both are connected to VDD, and it's going to give you the operation which is not required, or you can say that which is going to reduce the read margin. So in this particular thing, the read margin and hold margin are exactly same, or you can say little bit here and there, but it's going to be similar, right? So this is what we are calling 80 dual port. So dual port means one of the extra port will be there, which is from the read side. So you are not only writing, you are also reading. In earlier case, you are reading and writing from same line. Here, this is not the thing, right? Other than that, there is another technique where it's not about just reading. You can read separately, write separately. Other than that, but note that the 12T or 8T, we are targeting the low voltage operation, or you can say that because of low voltage, it cannot go to the required mode of conduction, and they might be in sub-threshold conduction. So they are also known as sub-threshold for the sub-threshold operation. So for the sub-threshold operation, we can use either 8T or 12T. So 12T will also have read and write separate lines, inverter, and 2 tri-state buffers, which has 3 states of output, right, which is known to you already: logic 1, logic 0, and high impedance. So that along with this transmission line gate or transmission gate, which take care of logic 1 and 0 both efficiently. So this was about 12T SRAM. This is also giving you opportunity for better read, write, and hold margins. Okay. There are further things like you need to know for such a sub-threshold conduction. You might have leakage. I don't want leakage, right? We don't want leakage. Leakage has to be minimum. But this leakage is happening during, when you are changing the state. Or you can say that whenever there is some dynamic changes are there. So the easiest thing is, if you want to reduce leakage, you can do 3 things effectively. Decrease VDD. If VDD is smaller, so the current drawn by VDD will be smaller. You can decrease VSS or ground, so that is also, I would say that it has to be increased, right? So that effectively you are going to have a smaller range of VDD and ground, right? And you can also do following things. Other than this, you can make negative VGS, you can make negative VPS, or VDS can be improved, so that all these things are going to reduce the leakage. Or you can say that in a way you are controlling the threshold voltage. If threshold is higher, then you don't have the leakage, or leakage will be the minimum one. So for that, we can use any of the following diagram, where word line, look at this. When there is a sleep mode, I'm going to introduce one more mode, which is known as the sleep mode. Instead of having word at VDD, I'm taking VDD line little bit lower than what was given to me. When you are doing this, of course, you are decreasing VGS, right? VGS is getting decreased. Yeah. Other thing is that bit line, which is also there, you can decrease that also, so that it's again, if you're decreasing this, it's again decrement of VGS. If you are not interested in all these, by the way, when you are doing all these things, it's also affecting the VDS also, by the way. Note that, right? And looking at the last option, which was changing the VBS, or you can say that the body to source voltage, if you want to control that, or if you want to decrease it, simply you can tune those values.